So we have two things to worry about on this slide. One is looking at experimental setup and trying to determine whether it satisfies a binomial condition and independent experiments. You're counting successes. The probability of success is fixed at p. What am I missing? I think that was that it. Let me read it here. So it said we need n experiments. Oh, each experiment ends in success or failure. That way we can count successes. The probability of success is p. You're counting the number of successes. Okay, so I'm checking 4 conditions. Fixed number of experiments, success or failure, probability of success p, counting successes. Here we go. Total cash won if you play quick pick lottery once every week for a year. Do we have a fixed number of independent experiments? Quick pick's probably n of them, 52 experiments. That's okay. Each experiment ends in success or failure. It doesn't. It ends with the amount of money you won, which could be nothing, or it could be $5, might be $20, might be a lot of money. So number 2 fails. So this is not success or a failure. So no, okay. The number of times you win a prize with quick pick once a week for a year. Okay, so now we've got a fixed number of independent experiments. Each experiment ends in success or failure. Prize or no prize. That makes sense. Probability of success changes or not changing over time. I think quick pick has the same probability of success every time, and you're counting the number of successes. All 4 are satisfied. Fixed number of experiments, success or failure as a consequence. Probability of success stays the same. Counting number of successes. Okay. Number of scratches in a randomly chosen car. Well, are we doing a fixed number of experiments? I don't see that happening. No fixed number of experiments. Number of cars with scratches and 20 random cars. Okay. Now I got 20 cars. The cars either have scratches or not. The probability of having a scratch could be about the same number. Are the cars independent? They're randomly chosen, so that makes them independent, I guess. We're counting the number. All 4 look okay. Number of cars. So a car is either scratched or not. The probability of having a scratched car over all cars probably is some number. Each car you chose randomly has that same chance of having scratches. That seems okay. The number of cars with scratches and 20 parked together. So here's the problem here. So if you do this experiment, 20 cars are parked together, and you count how many cars have scratches, maybe someone walked down that parking lot and it just keyed all those cars. Could have happened. That happens in these cars too, but a certain fraction of cars overall are scratched. Some of them are keyed that way because someone decides to do malicious stuff to cars all in a row, but here we're picking cars in rows. So if I pick another 20 cars, probably the probability of being scratched could be completely different just because it's a different neighborhood. And in different neighborhoods you have different percentage of scratched cars or different levels of people going out and scratching cars just for fun. So I would go, the P might change. P may change by location. Since you're picking 20 together. And then, so no. Okay, so no, okay. Number of classes you get an A in the semester. Well, let's see. You have a fixed number of classes, so that's a fixed number of independent. Are they independent? You could think they are. Each experiment ends in success or failure, A or not. The probability of success is a constant number P. Well, I doubt that you have the same chance of getting same chance of getting an A in every class. So I'm going to go P changes by class. So no. Okay. That was hard. And over here is the way of analyzing that stoplight problem that we saw in general. So if we have a binomial experiment where n experiments are performed and p is success probability, and we're counting successes, I'll write that here. X equals number of successes. So we're worried about what's the chance of getting k successes. So here's the story, right? So you imagine this n experiments laid out like this. I'm thinking of them as if they were stoplights. And then I have to put in place k successes. So success and stop look kind of the same. And the rest of them, I guess we could call them failures. So the patterns where there's k of them, of n, like that, the number of patterns we know as nck, like that. So for k successes, the k successes that is placed in this list of n experiments, there's this many ways to do it. In each of those patterns, the probability would be p to the k, because there's k successes. And here's the failure probability, 1 minus p is the n minus k. So if n was 5, you have 3 successes, 2 failures. That'd be p to the third, and 1 minus p squared would be the probability of any of these strings that look like this with k successes among n. So what we're going to do is combine the counting problem with the independence problem. Here's how many patterns there are, and here's the common probability for all of them of that size. That's that where you have k successes in n experiments. They all have this probability. So I put this number in front. That's how many of them there are. And so we would add these this many times. And so instead of adding them this many times, I just take this times that, and that does that job. So since those different ways of spreading out the successes correspond to disjoint outcomes, we would add all the probabilities, but since they're all the same number, we just multiply by how many there are. And so that combines disjoint with independence with counting. How do you like that? The best thing ever. So there's different ways of writing that down. So we know that this NCK, for people that have seen other math topics, they might have seen it look like this as a binomial coefficient. These are equal. And then maybe we want to write down the probability function like this. So we want to use x there. Then we'd stick the x here and up here and over here. And the first number there counts the number of patterns, and the second number counts the common probability. And that allows us to compute binomial probabilities pretty easily. So I've got a way to do this on my calculator, and that's not hard to do. And so we'll be doing that shortly. And this is an exciting time because we get to combine a lot of ways of thinking into something that's quite useful, as we'll see in a minute.